Hi, my name is Ozan and we will be together in the following weeks in the electromechanical and energy conversion course. So, you can visit my website. I'm planning to put the presentations on the website, and also we will upload the videos to YouTube and audio class as usual. So today we will talk about the control and operating modes of the DC motors, DC machines, but let's do a quick review, before getting into details. So again, we as electrical engineers, we like to put things in simple models, and actually there's a famous saying that like all models are wrong, but some are useful. And again, let's say it's not 100% accurate for any DC machine, but it is useful during modeling and simulation of electrical machines. So generally, electrical machines can be represented as a voltage source, which is proportional to speed, as we will see, and they are connected with a resistance, which is the armature resistance, and the usual convention is like that. So this is, we have the EA, so that's also called like the back EMF, or that is the induced voltage with respect to rotation of the rotor. And again, that back EMF is generated due to some flux, and that flux, as we have seen in the previous weeks, can be generated by a separate winding, like as the separately excited DC machine, or it can be excited using a series winding, parallel winding. There are like different types of DC machines. But anyway, let's put that aside, and we have a back EMF, and then we have a armature resistance, and again those machines are not 100% efficient, so we have some losses in the machine, and these things are IA square RA losses, armature losses, and again it is not shown here, but there are the field winding losses, although the most dominant one will be the armature losses. And again we will see in the following weeks that there's also like a inductance connected to here. I mean, it's not a separate inductance, of course, it's inductance due to the windings of the armature. But anyway, then we have the terminal voltage, and you can connect the voltage source, and again it can be either in that side or in the other side depending on the operation mode. So that is the simplest model of a DC machine. And again, if we just review what we did in the previous weeks, you can represent the induced back EMF voltage EA, as a function of the flux per pole. Okay, so this flux per pole, and the important thing is that back EMF is proportional with speed. So if there's no speed, there's no induced voltage, and as the speed increases under constant flux, the back EMF voltage also increases. And Ka is a machine's constant depending on the size, power rating, and that kind of thing. So that is the armature constant. So what the important thing that you need to remember, again, that flux can be generated by a separately excited winding or a series winding. But if they are working under constant flux, then we can say EA is proportional with speed. Okay, the higher the speed is, the higher the back EMF in that waveform. So that EA is here. Again, there's a important thing. We don't have like separate devices for motoring or generating. We call them like electrical machines or DC machines, and motoring and generating is just a mode of operation. And if you are in the motoring action, then electrical energy is converted to the mechanical energy. But however, if you are working in the generator mode, then mechanical energy is converted to electrical energy, and that is determined by the direction of the armature current, and the direction of the armature current is determined by the relation between terminal voltage and back EMF. Okay, so the important thing is there's no difference between a DC motor and a generator. So we used to show it in the classes, like you can try it yourself, but now let's show it through a video. So here we have electrical machine. So what you do is you just rotate it, and it generates some electricity, and you have the LED lights up. Then actually you can connect these two identical electrical machines to each other. I don't know if you can see from me. So actually you rotate one of them, and then the other one is directly rotated, because the one that you rotate behaves as a generator and it produces some electricity. Then you connect the other one, which is basically running as a DC motor. Actually this is how our all civilization or all the electrical machines are running. So we have hydroelectric dams or other power generator units, and we are generating electricity there, and we are bringing that electricity back to our cities. Then we connect our loads, our whatever machines we have. Okay, so then the other one is rotating, or you can still rotate the other one, and there's now a gearbox, and now when you rotate that thing, that can be rotated much faster, or you can have that one. Okay, so as you say, it is just a mode of operation, so it is basically determined by the relation between terminal voltage and back EMF. Okay, so then again, as I said, if the flux is generated by another coil, then you have the field winding, so it can be represented like that. And the field winding, okay, again assuming it is under linear mode, so there's no effect of the saturation and that kind of things. So IF will be proportional with flux per pole, so you can control the amount of back EMF by controlling the field winding, and we will talk about those techniques in the next presentation. So again, if our terminal voltage, if the applied voltage is larger than back EMF, then the current direction is like that, so that is in the motoring mode. Or if it is less than that value, okay, if it is less than that value, then the current will be flowing from EA to the terminal voltage side, and that will be the generating action. Of course, in the motoring action we are transmitting power from our terminal side, but if it is in the generating action, then we are transferring power from our mechanical system to electrical system. Okay, but in any case, of course, we don't have efficiencies larger than 100%. We will also, have the losses, and those losses will be proportional to the square. So it is always dissipating some heat. So even if it is the current is flowing in that direction or the opposite direction, we will all have the armature losses here. Okay, so again, on top of that, you can have the IF field windings losses like that, but compared to those ones, these losses are mostly negligible. And again, if you are using like a small electric motor that you can find, they are mainly the flux is mainly generated by a permanent magnet, and in that one you don't have any external windings and you don't have any losses on the field winding. So let's ignore it for now and let's focus on that side. So we have on one side the electromechanical power, the power that we are transferring to the mechanical system, and then we have the armature power, so the all power transmitted to here, and we have the armature losses. Okay, so again in this case it is working as a motor, so this is for the motoring mode. So the output power, for output power, you have the motor, okay, so you have the motor, you have the shaft, okay, then you have the P in, which is the electrical power, you have the P loss, which is the losses in the thing, and then P out is the mechanical power that you are sending to the mechanical system. So the input power is VA times IA, and since we are talking about DC power here, and there's no power factor or that kind of things, so as we had in the transformers or AC systems, so that is our input power. Then we have the, I think I have written it wrong, so there needs to be a square here. Then you can have the losses for the armature, and it is written like that. I will fix it in the presentation. Then the output power, I mean, if you subtract that one, if you have that losses as the I square RA losses, then that thing is the link between our mechanical system. So that is not a really voltage source or anything. I mean, that is how we transmit power to the magnetic and then the mechanical system. And we have the IA here and with the EA, so that is power converted to mechanical system. Okay, so then if you think about that, let me draw that motor again. So we have the motor and we have the shaft. So we have VA and we have IA getting in. So at the output we are doing some work, and then that is how we basically have torque and speed, and P mechanical is equal to torque times omega. Okay, so let me write it here. Of course, if you can remember it from your physics lecture, so I can write F, for example, in the linear system, power is equal to force times velocity, right? So it is meter per second, and this is Newton, and when you multiply that one, you have the watts, and that watts is the same watts as we have the electrical energy. And again, this is for linear systems. And in the rotational system, okay, what we have is, instead of force, now we have torque. So this is now Newton meter, and instead of the linear speed, we have rotational speed. This is radian per second. So again, that gives us the power. Okay, so that is watt. Okay, so that is identical to the one in linear system. So again, if you write, if I say our mechanical power is torque times omega, then that is equal to EA times IA, the energy transferred to the mechanical system. So I can rewrite these two equations, and I know EA, I mean, from the previous slides, I know it is KA times omega times flux per pole times IA. Okay, then you can, these two can cancel each other. So what you end up is those things, and you have the torque. Okay, again, if it is a permanent magnet machine, or if it is a separately excited DC machine but under constant field current, then that means that one is constant, and that is also constant, that is with respect to machine parameters. So then you have other important relation. Okay, the torque of an electrical machine or a DC machine is proportional to current. Okay, T is proportional to armature current. So the more current that you can send, the more torque you generate. Of course, in order to send more current, you need to apply more voltage, and we will talk about those things in the control of DC machines. Okay, so again, you have torque is proportional to current. And again, the next question that you can ask is then what happens to a DC motor at startup? So let me write the equivalent circuit again. So I mean, it's like simple equivalent circuit, let's say EA, and then we have VT here. Okay, this is RA, this is current. Okay, so of course I can write IA. Okay, IA is really easy, VT minus EA divided by RA, right? Really simple. And I know torque is proportional with the current. So the question is, then at startup means when the machine is just started or when it is at stationary. So it is when the speed is 0. Okay, so if its speed is 0, then what was EA? Let's write it again. KA times omega times flux per pole. Okay, so if that one is 0, then that means EA is 0. So as you just start the machine, the speed is 0, and since at the end of the day it is in the armature, you have the coils, and if they are not rotating, you have the field flux, but the voltage is induced with due to change of the flux, and if there is no rotation, there will be no change in the flux. So because of that you have no voltage at the back EMF, and if there is no voltage here, so IA, okay, will be equal to VT divided by RA. So usually RA is, let's say, 0.1 ohm, and let's say VT is, I don't know, 24 volts. Okay, so armature resistance is really small resistance because it's not a separately connected resistance. It's just the resistance of the coils in the winding, and it is copper, and it has low resistance. So for example, in this case you are talking about currents up to 240 amps, so that creates lots of current if you just apply a terminal voltage directly, and because of that you will have like really large currents at the startup. So that can be a good thing and that can be a bad thing. The good thing is the more current you have, the more torque that you generate, so electrical motors can able to produce like really high torques during startup. And the bad thing is your voltage source should be capable of giving 240 amps like in this case, or you can damage your voltage source, or you can accelerate in an uncontrolled manner. So somehow you don't want to connect your source voltage directly to the DC motor, but you want to have some controllers in between, and we will talk about the methods of control in the next slide. But let's talk about the advantages first. Okay, so again these are the same thing, and so this is a result is like you never attempt a drag race with an electric car. I mean, electric cars are quite popular nowadays, and most of them, and I will show you those things like Tesla or BMW or whatever brand, they are using like AC electrical machines, but that one, the white zombie, is using a DC motor. Okay, let's look at inside of the white zombie. So here you see white zombie, so it seems like an old car. I don't know what brand is it. It seems like a Corvette or other one, the black car. I think he's like really sure to win that race, but let me pull it back. So I mean, it produced like enormous amount of torques, so at the end of the day it can get up its wheels, and it's clearly winning the race by a far margin. Yeah, by the way, you can check those links in the website, and they are available I think in YouTube as well. So let's move on. So again, this is a specifically made electric car with DC machines and a large DC batteries, but it is really similar to what we have in normal commercial electric cars. And here you have a Model S, I think one of the most popular electric cars from the Tesla. We have
the rear Model S,
the Tesla Model S. I think now they have more up-to-date versions, but just have a look at what's under the hood. So you have the electric motor on the rear wheel, and next to that one you have the power electronics. Okay, so they are connected together, and you can control it. And let's have a look at, I think they will also show what is inside that
the
motor.
Consists of two parts.
Right.
The rotor.
So here
and the
you have
your
the
aluminum.
rotor and you have the stator. Again, this is not a DC machine. This is an AC machine. So if you choose to take the Electromechanical Energy Conversion 2 course in the next semester, we will talk more detailed about these induction motors. But anyway, the idea is same. So you have a rotating part, and in the stator you have some coils. So that's a cross section, and you know that's generating some part. And this is your connection to the wheels.
Brushless AC motor.
I think it is 290 kilowatts. Again, I think they updated a couple of versions with a more powerful motors. Okay.
It's an alternating current.
So it is a 4-pole, you know, 3-phase induction motor, and it uses alternating current, and you have the power electronics to control the torque. But the idea is, you know, really similar that what we have with the DC motors. So the more, you know, current that you can send to the power, it can generate the torque really quickly, especially during startup. So it gives them, you know, huge advantages over internal combustion engines, because in the internal combustion engine you put your feet on the gas pedal, then the injector sends some fuel, and they get some air, and then piston starts moving up and it generates some torque. You need to change the gears to operate the internal combustion engine in the most optimum condition. But that is not the case with an electric motor. You have the power electronics controller, you have the battery, and you can instantaneously send the amount that you want. And once the electric machine have that current, it generates the torque instantaneously, you know, due to the, you know, magnetic circuits, magnetic relations inside the electric motor. So let's have a look at what does it mean for Tesla Model S. Again, you know, there are, you know, different hundreds of videos of the drag races of electric cars between other ones, and if you are looking for some video, I, you know, advise you to have a look at those videos as well. And I will show you the one with the, you know, Tesla versus the Bugatti Veyron. And Bugatti Veyron is like I think it's one of the fastest cars, and it's, I think, over 1,000 horsepower, 6-liter engine or something like that. Then you have the Tesla. You know, at the end of the day, it is a 4-door, you know, like family car. It is not, you know, custom made or nothing. So it is mass-produced electric car. So let's have a look at. Okay, I think they're ready. Go side, and it's happening the same thing. You know, electric car just moves on, and that's like faster acceleration from Bugatti. But then, of course, you know, Bugatti is a more powerful car, so it catches up, it wins the race for that one. But again, you know, check for other videos. But important thing is, again, you know, you have the capability of generating that torque instantaneously. So during startup, you know, all electric cars and, you know, that kind of machines have the advantages of generating instantaneous torque if you have a voltage source capable of giving enough current. Okay, so, you know, that was a quick summary of the electric machine. So the first thing that you need to remember is, like, back EMF is proportional with speed. Of course, you have the control over the flux as well. And then secondly, the torque is proportional with current. Okay, so again, you can, you know, control the flux just to control EA and torque, and that is, you know, one of the methods of control of DC motors, as we will see in the next video. Okay, so you can download this presentation from this link from my course webpage, and also I will put it on the OT class as well. Okay, thank you.